To actually be able to consider dimensionalism a grand unified theory of everything, we'll need to express the fundamental forces in terms that somehow predict the null hypothesis of quantum gravity and give good reasoning why we shouldn't expect to find it. If this is the first video of mine on dimensionalism you are watching, I recommend that you start by watching the dimensionalism playlist from the beginning, as important disclosures are given in the first video to be forthright about my ingenuity, well, as forthright as I can be. And also, the logic of the previous videos is built upon here and in later parts, so continue viewing at your own discretion. But the TLDW is that I am not a physicist nor a mathematician, and I can accept that this theory is in a superposition of states between science and pseudoscience, as dimensionalism cannot predict much other than remain as a null hypothesis to other theories, with a few predictive statements like you will not find the graviton, or you will not find any strings at the base quantum level, or even as I explain later in this video, you won't find a boson that is a force carrier for dark energy. So with that in mind, take what I say here with a skeptical grain of salt, and as always, think for yourself. Now that we actually have the fundamentals down, we can now consider the fundamental forces. Understanding the fundamentals of reality in the form of the dimension types and quantities is important to understand that there is no such thing as quantum gravity. You heard me right. Gravity is not a fundamental force. That is what I predict anyway. Within atomic and subatomic interactions, there are 6 or 7 things that go on at that level that are knowingly needed to consider everything. Here's a picture explaining these 6 or 7 phenomena going on in the atom. We'll start with the most obvious phenomena that are already known forces already accepted as fundamental. In purple over here, we can see the electromagnetic force at work. The protons repel each other right here. The protons and the electrons attract each other over here. And also depicted here, up in the corner, are electrons repelling each other against the electron clouds of nearby atoms. Over here, in light blue, we can see the strong nuclear force at work. Right here. Holding quarks together with gluons to hold together stable protons and neutrons. Here's a proton, here's a neutron. The dark blue squiggly lines show the residual strong nuclear force, and it holds together protons and neutrons right here, and between it also holds together neutrons and neutrons. This clarification is needed is because the residual strong nuclear force between two protons is counteracted by the electromagnetic force. That's why I didn't put a blue squiggly line between the two protons, because it is there, it is just heavily counteracted by the electromagnetic force. This may be a new way of thinking about the strong nuclear force, but a good way to remember that it is strong is that if you think about the inside of a proton, there's also the electromagnetic force that is going on between the quarks inside of the proton or the neutron. So you have the electromagnetic force going on between different charges of the quarks. So it takes a really strong force to keep these differently charged quarks in close proximity to each other. Onward to green over here, I represented the causal changes that can occur from the weak nuclear force. Particles undergoing these changes require the two W and one Z bosons to evolve between a neutron and a proton, as shown here, or between a proton and a neutron over here. This weak nuclear force is also important to allow atoms to decay into alpha and beta particles. In orange up here, I tried to represent the force that results in the individual particles obtaining a stable mass. The logic being, if particles have mass individually and set apart from other forces, there is an equivalent amount of energy going on to give these particles their mass. I propose here that this is in and of itself could be the currently eluded Higgs Force that has been glossed over by physicists. Fun fact about that, did you know that 99% of mass comes from the other forces that are not the Higgs Force, and only about 1% of the mass comes from the base mass that the elementary particles inherently have? If you wanted to see how much you would weigh if the Higgs Force was the only force that gave you mass, you could multiply your weight by 0.01 to get an approximate answer. I thought it was pretty cool the first time I learned that. In red right here, we can see individual quarks being caused to spin because of their charge. I'll need to cite Jeff Yee's energy wave theory to adequately answer this one, to start answering why gravity is not a fundamental force here. To quote, "Gravity is not a separate force or particle. It is simply the lost energy/amplitude as a result of particle spin that becomes magnetism. Gravity is a shading effect due to unequal amplitude. When two particles interact, the electric force typically dominates. In matter, where protons cancel out the waves of electrons, the effect of gravity begins to take over." So particle spin is just the residual magnetic force from the electromagnetic force, but the shading effect from the spin may be the source of what produces gravitational waves, when there is enough matter in the center of the body to cancel out the standing waves the electromagnetic force produces. Assuming I understood this correctly, if gravitational waves are a shading effect, they are then not the result of a primary force, but are in fact a result of a cumulative secondary force. Gravity's secondary nature can be elaborated on by acknowledging that the total mass of the atom is the result of the accumulative weight produced by all of the primary forces in the atom. And particle spin is also related to the phenomenon of helicity in the particle, which compares the momentum of the particle to the way it spins. And lastly, I don't even know if you can see it or not, but all over the board I have these yellow squiggly lines. And I was honestly at a complete loss of how to represent this force. The dark force. No, this isn't Star Wars or anything. It is basically what I have tried to do to explain the force of space increasing between two objects. This dark force describes how we live in an observable universe that, on one hand, is observable to 46.508 billion light years away, but on the other hand is only 13.8 billion years old. There's a 32.708 age discrepancy there. And unfortunately, the best way I can use right now to describe what is happening with the dark force is the division by zero that I explained in part 1. With the dark force's dimensions being volumetric space divided by zero, which is equivalent to infinity times volumetric space. This force happens in all places at once, even in our bodies and in the planet. We don't feel it, see it directly, or are capable of measuring it at the moment because the force itself is really tiny locally and is negated by the other four primary forces of nature. But if you put enough space between two objects, far enough away that none of the other primary or secondary forces of nature can interfere, the amount of space between the two objects would multiply exponentially, creating new space to undergo the same division by zero. And what we see as observers amidst one of these gigantic galactic objects is an acceleration of the universe, i.e. dark energy. If a stable point of space must move from its point of nothingness, it'll move away from its point of origin, only to be replaced with another point of space in its wake. There is no end to space, assuming time also has no end. So with this model, the universe is simultaneously finite and infinite in size. Finite from any particular point in time, with the distance being exponentially proportional to the amount of time the first point of space has had time to duplicate, but infinite when time is also unbounded. And we'll get into that aspect more in a couple weeks. So let's build a logical pattern linking these 5 deduced primary forces with their primary dimensions. The Higgs force interacts with the Higgs field, which gives us particle mass from the Higgs boson. The electromagnetic force interacts with the electromagnetic field, which gives us fundamental electric currents from photons. The dark force interacts with space, which gives us fundamental length. If fundamental length is larger than zero, a permeaton boson might be found, but this current model predicts that a zero-dimensional point is the fundamental space, therefore not needing a boson to create more space. The Planck length is an acceptable stand-in for a value of fundamental length for measuring purposes, however. The strong nuclear force interacts with the causality field to give fundamental causality, or fundamental time, but saying fundamental time in this instance isn't really accurate. Time is more of a relative and steady representation of the causality field. Anyways, this causal force is carried by gluons. And lastly, the weak nuclear force also interacts with the causality field and is carried by the W positive, W negative, and Z bosons. So to make the final argument that gravity is not a primary force, let's explore a couple of other secondary forces to help compare what gravity does. A secondary force of water interacts with all of the fields, which produce water waves, but there is no water boson. The secondary force of entropy interacts with the space and the Higgs fields. It is like particle radiation, and it produces compressional waves when it's really strong. There is no entropic or compressional boson, however. The secondary force of gravity interacts with all of the fields and gives us gravitational waves when it's really strong, but there is no graviton. Is this a fair assessment? Leave your thoughts in the comment section below. In conclusion for that point, not every wave that we see has a boson carried in that wave. Just because electromagnetic waves are linked with the photon particle does not necessarily mean that the gravitational waves will be linked with the graviton particle. I was also hesitant to confidently say that gravity is in use with all of the primary forces, since it may not be affected by the dark force at all, or the length dimension. And the energy wave of the origin of the gravitational waves comes from the particle spin, which comes from the electromagnetic force, and then the combined forces of the rest of the atom are used to make the mass, which would be in the top of gravity, and then it is proportional to the distance squared. So actually all of the dimensions are there, I just had to speak it out first. Now going back to this new dark force, I did have a couple of concerns about it. One, we cannot observe it up close, and we don't have the microscopes or measuring tools nearly that strong yet. And two, it is only called dark because it is so mysterious to us. And Space Force was already taken, and probably wouldn't be taken seriously if it was named such. And three, it's space. Trying to measure how much space is between two objects requires an object to measure it. The dimensions don't have clearly solid manifestations of themselves that we can use to measure things. We can only measure length when we have something else as a stand-in representing what that length is. And since the dark force is so weak, and I again propose this coming out of a 0D point of space, a boson for this force may not exist. And if this is the case, and I am also correct in deducing that the graviton also does not exist, the list of discoverable and probable future bosons is near nil. And that is all for this episode. If you like thinking freely and critically over a larger variety of topics, we can help each other out. I will keep making videos, and you can do me a giddy and click on those like and subscribe buttons. Please? And join our group of sea creatures who live in the Notion Ocean. Kumbaya, mother duckers.